Now, here I have given name of three molecules. One is 2-bromobutane, the other one is hexane 3-ol, the third one is 3-chlorobutane 2-ol. So 2-bromobutane. So butane means 4 carbon atoms. If you number from here, 1, 2, 3, 4. Okay. And 2-bromo in second carbon atom has bromine atom. Okay. So that is 2-bromobutane. And if you try to identify a chiral center or stereogenic center or chiral carbon here, so what is a chiral carbon? 4 valencies are satisfied by different groups. So here, this is a chiral carbon. You can see that. For example, if you take this carbon, the first valency is satisfied by CH3 group. The second valency is satisfied by the bromine atom. Third valency is by this hydrogen atom, and fourth one is by the CH2 CH3 group. So that means all the 4 valencies of this carbon atom are satisfied by different atoms or groups. So this is a chiral carbon, and in this molecule there is only one chiral carbon. If you take this carbon atom, it has 3 hydrogen atoms. That means 3 hydrogen atoms are same. So its 4 valencies are not satisfied by different groups. So this is not a chiral carbon. This is not a chiral carbon because it has 2 similar atoms, and this is not a chiral carbon again. So here only we have only one chiral center or chiral carbon atom. So this will show definitely optical isomerism. And if you take hexane 3-ol, here also there is only one chiral center or only one chiral atom, which I have marked here. And the third molecule, which is 3-chlorobutane 2-ol, here, if you examine this molecule, you can see that there are 2 chiral centers because this carbon atom has a methyl group here. So one valence is satisfied by methyl group, the second valency is by OH group, and third valency is by hydrogen, and the fourth one by this whole group. This carbon atom also has 4 different valencies. I mean, this carbon atom, its 4 valencies are also satisfied by 4 different groups. So therefore, that carbon atom is also a chiral carbon. Okay. So, so all the red star marked carbon atoms are chiral centers. Okay. So take, for example, this 2-bromobutane. If you take 2-bromobutane, for example, so I represent one of the isomers of 2-bromobutane like this. This is a special kind of representation, what we call the Fischer projection. Okay, so you can, Fischer projection is to represent a 3-dimensional molecule in a 2-dimensional plane. So that makes our discussion easier. So here, this chiral carbon is actually at the center of this cross. So this is the chiral carbon. Okay, so which is this carbon atom. Okay, and that carbon atom has 4 other groups. Let's see what are the groups. Okay, it has a CH3 group, which is here. It has a CH2 CH3 group, which I have shown here. C2H5 means CH2 CH3. This carbon atom has a bromine, which is here, and hydrogen, which is here. Okay, so this is 2-bromobutane, and this junction is the chiral carbon atom in 2-bromobutane. Okay. Now, how you can show a Fischer projection is, we know that this is a sp3 carbon atom, so the shape is tetrahedral. And if you keep this molecule where 2 atoms are projecting towards you, then definitely the other 2 projecting backwards you. So the atoms which projecting towards you will be in the horizontal positions. Okay. The other atoms will be in the vertical position. So that's how we convert a 3-dimensional structure to a Fischer projection. Okay, so anyway, I mean, you don't have to worry about that. That is a little bit more complicated stereochemistry. So anyhow, my point is you can represent a 3-dimensional molecule in a 2-dimensional plane by using Fischer projection. So this is one of the isomers of 2-bromobutane. And if I'm keeping a mirror plane here and I'm taking its mirror image, which will be like this, these 2 are non-superimposable these two are non-superimposable mirror images, and they are isomers because these two are different molecules, but they are isomers. One isomer is dextrorotatory, D or plus, and the other isomer is levorotatory, L or minus. Okay, so this is how we write the structure of the isomers. So one of them will be dextrorotatory, the other will be levorotatory. Okay, and so the relation between these two isomers they are non-superimposable mirror images. It's very important. So they are non-superimposable mirror images. We call it as enantiomers or enantiomorphs. So what is enantiomer or enantiomorph? Enantiomers are stereoisomers, definitely, because we are discussing about the stereoisomerism, and optical isomerism is one of the stereoisomerism. So an enantiomer or enantiomorphs they are stereoisomers which are related as non-superimposable mirror images. So if any two stereoisomers has a relation like non-superimposable mirror images, then that is called the enantiomers or enantiomorphs. And this phenomenon is called enantiomerism. And enantiomers are optical isomers because they are non-superimposable mirror images, means that those molecules do not possess a plane of symmetry or mirror plane. That means they are disymmetric or they are chiral. So that means they will show optical isomerism. So enantiomers are optical isomers. Okay, so if you take an enantiomer, one of the isomers will rotate the plane of the plane polarized light towards right, and the other isomer will rotate the plane of the plane polarized light towards left to the same extent. If you mention the specific rotation, then the D isomer, dextroisomer, will rotate to the right, and the levo isomer will rotate to the left to the same extent. So in that case, if you take an equimolar mixture, means same concentration of D form and L form together, so what will happen is the D form will rotate the plane of the plane polarized light to the right. At the same time, L form will rotate the plane of the plane polarized light towards the left. So that means the rotation gets cancelled. So the mixture will be optically inactive. So optically inactive because both rotations got cancelled. That mixture is what we call the racemic mixture or racemic modification. So racemic mixture or racemic modification is nothing but an equimolar mixture of two enantiomers of a substance. And this mixture will be optically inactive due to external compensation, because the rotation by one isomer will be cancelled by the rotation by the other isomer. So that's what we call the racemic mixture of racemic modification. So here I have shown another example that is for 2-butanol or butan-2-ol. So here what I did is the tetrahedral geometry, I have keep the molecule, two of the atoms are projecting towards you, and the other two automatically towards the back side. And I take, this is the plus or D form of 2-butanol, and I take the mirror image of that one. It will be like this. OH will be here, C2H5, H will be here. They are non-superimposable mirror images, or they are enantiomers. So this isomer will rotate the plane of the plane polarized light towards right. That's why it's denoted as plus or D form, and this molecule will rotate it to the left. Okay, so that's why it's denoted as minus or L 2-butanol. So if I try to show the same molecule in Fischer projection, so this will be the Fischer projection. So what I did here is, so the group which projecting towards me, I shown it in the horizontal plane. So OH is here, H is here, then CH3 is here, C2H5 is here, and I take the mirror image of that, then I will get the L2-butanol. So you can represent the optical isomers either in this form or in this form, which is convenient for you. You can adopt that method. Okay. Now, what will happen if a molecule has more than one stereogenic centers, or more than one chiral carbon atoms? So in that case, if N is the number of stereogenic centers or chiral carbon atoms in a molecule, then the possible number of stereoisomers is given by 2 raised to n. Okay, so if you take, for example, 3-chlorobutane-2-ol, we know that in that molecule we have 2 chiral centers or 2 chiral carbon atoms. Okay, so in that case, the number of possible stereoisomers are 2 raised to n, 2 raised to 2, because it has 2 chiral centers. That is equal to 4 stereoisomers. So 3-chlorobutane-2-ol has 4 stereoisomers. Let's see how we can represent these 4 stereoisomers. So I'm starting from 1. Here what I did is, so one junction is the first chiral carbon, this one, and it has methyl group. So methyl group is here, hydrogen is here, OH is here, and the fourth one is the whole group. That whole group is here. Okay, and this is the second chiral carbon, which is this junction. It has Cl is here, methyl group, which is here, and one hydrogen atom, which is here. The rest is this whole group, which is here. Okay, and this is the erythroform form because the hydrogen atoms are on the same side. So this is the erythroform of 3-chlorobutane-2-ol. Okay, so this is one of the stereoisomers. So in total, we have 4 stereoisomers, and this is the one of the stereoisomers. And if I take the mirror image of this one, that will give me the other isomer. Okay, so it's very easy. So this is the mirror image of this representation, which are non-superimposable mirror images, structure 2. And so we have 2 more structures for that. Now what I did is I arranged hydrogen atoms in opposite directions. So this is the other isomer. So that is trioform because hydrogen atoms are in opposite sides. So this is trioform, that is structure 3. And to get structure 4, what I have to do? I have to place a mirror plane and take the reflection. So this will be the structure 4, and these 2 are the other isomers of 3-chlorobutane-2-ol. So we have 4 stereoisomers of 3-chlorobutane-2-ol here. Okay, so now let us examine each isomer. So structure 1 and structure 2, they are related as non-superimposable mirror images. Okay, so they are enantiomers. Okay, then they are erythroenantiomers. Now, if you examine structure 3 and structure 4, they are also enantiomers. We call it as trioenantiomers, structure 3 and structure 4. Okay. How about structure 1 and 3? What is the relation between structure 1 and 3 and structure 2 and 4, or structure 1 and 4, structure 2 and 3? Okay, so they are stereoisomers, but they are not mirror images. For example, if you take structure 1 and structure 3, they are stereoisomers, but they are not mirror images. Or structure 1 and structure 4, they are stereoisomers, but not mirror images. Structure 2 and structure 3, structure 2 and structure 4, all are stereoisomers, but not mirror images. We call these kind of relation as diastereomers. Okay, so what is diastereomers? Diastereomers are stereoisomers which are not mirror images, and enantiomers are stereoisomers which are non-superimposable mirror images. So it's very important. Okay, so if you try to differentiate between enantiomers and diastereomers, enantiomers are non-superimposable mirror images, whereas diastereomers are not mirror images. Then enantiomers are optically active. Of course, they rotate. One isomer rotate to the right, the other isomer rotate to the left. So enantiomers are optically active. Diastereomers may or may not be optically active because diastereomers are stereoisomers. All stereoisomers do not show optical isomerism. So diastereomers may or may not be optically active. And enantiomers show equal but opposite specific rotation. For example, if you take an enantiomer pair, one isomer will rotate the plane of the plane polarized right to right. The other isomer will definitely rotate to the left. So show equal but opposite specific rotation. But if the diastereomers are optically active, they show different specific rotation because diastereomers are not the same pair of isomers. So if they show optical activity, they show different specific rotation. Okay, the enantiomers has almost similar physical properties and chemical properties, whereas diastereomers has different physical and chemical properties. And enantiomers can form racemic mixture. If you take equimolar mixture of D form and L form, that form racemic mixture, whereas diastereomers can't form racemic mixture because they are totally different molecules. So these are the the differences between enantiomers and diastereomers. Okay, so for the time being, I'm stopping here, and we will discuss the optical isomerism in lactic acid and tartaric acid in the next class, and that will probably our last class from the stereochemistry module. Okay, so thanks for listening to the lecture.